Imagine building the most powerful computer in the world, not by etching silicon, but by arranging individual atoms one by one into a perfect, flawless crystal. This isn't science fiction. It's happening right now in labs across the globe, and it's the foundation for the quantum computing revolution. We're on the verge of creating machines that could solve problems currently impossible for even our mightiest supercomputers. From designing new medicines to creating revolutionary materials. But the architects of this new era face a challenge of immense precision. They are building the heart of these machines, atom by atom, where perfection isn't just a goal, it's a requirement. To understand why, we need to talk about qubits. Your phone or laptop uses bits, which are tiny switches that can be either a 0 or a 1. A quantum computer uses qubits. Thanks to a bizarre property of quantum mechanics called superposition, a qubit can be a 0, a 1, and both at the same time. When you link qubits together through another strange phenomenon called entanglement, their computational power explodes exponentially. This is the source of the quantum advantage. There are many ways to make a qubit, but one of the most promising candidates is the neutral atom. Why atoms? Because nature has already done the manufacturing for us. Every atom of a specific element is a perfect, identical copy of another, free from the tiny imperfections that can plague man-made qubits. To build a computer from them, scientists use a tool straight out of a sci-fi movie: optical tweezers. A highly focused laser beam creates a tiny trap of light that can grab and hold a single atom. By creating a grid of thousands of these light traps, scientists can assemble vast arrays of atoms, each one a potential qubit, arranged in precise, programmable patterns. This flexible architecture is key to tailoring the computer for different tasks. But before you can place an atom into a tweezer, you have to catch it. At room temperature, atoms are zipping around at thousands of meters per second. To tame them, scientists use a device called a magneto-optical trap. It's a complex chamber that uses 6 intersecting laser beams and a magnetic field to create a kind of optical molasses. As an atom moves through this field, the lasers push against it, slowing it down dramatically. This cools the atoms to just a few microkelvins, a fraction of a degree above absolute zero, the coldest temperature possible. The result is a dense, cold cloud of atoms floating in a vacuum, ready to be loaded into the computer's architecture. Now for the big problem. When you turn on the array of thousands of optical tweezers, the atoms from the cold cloud fall into them randomly. Each tiny light trap has only about a 50% chance of catching an atom. The result is an array that's riddled with holes, a disordered, partially filled grid. These missing atoms are called defects, and they are a complete showstopper. For a quantum computer to work, all its qubits must be present and able to interact in a precise, coordinated dance. A single missing atom breaks the chain, corrupting the calculation and rendering the entire algorithm useless. Imagine trying to run a complex program, but half the memory chips are missing. It simply won't work. For quantum computing, achieving a 100% perfect defect-free array isn't just a nice feature, it is an absolute non-negotiable necessity. So how do you fix this messy random grid? The first solution, pioneered a few years ago, was elegant in its simplicity. Move the atoms one by one. Scientists would first take a picture of the array to see which traps were full and which were empty. Then, they would use a separate, steerable optical tweezer, a sort of atomic crane, to pick up an atom from a filled trap and carefully move it to an empty spot. They would repeat this, atom by atom, shuffling them around until the target area was perfectly filled. This atom-by-atom assembly was a monumental breakthrough. It proved that perfect atomic structures could be built from the ground up, and it allowed for the first creation of defect-free arrays with hundreds of atoms. But it had a fatal flaw. It was incredibly slow. The time it took to rearrange the array scaled with the number of atoms. For a few hundred atoms, it was manageable. But for the thousands or tens of thousands of qubits needed for a useful quantum computer, this one-by-one shuffling would take far too long. The clock is always ticking, as atoms can eventually escape their traps. If the rearrangement process is too slow, you just end up with new defects. To overcome this speed limit, researchers turn to a new strategy: parallelism. Instead of moving one atom at a time, why not move many? This led to the development of clever algorithms to optimize the atomic shuffle. One approach was nicknamed the Tetris algorithm. Much like the game, it works by moving entire rows or columns of atoms simultaneously, sliding them into their correct positions much more efficiently. Another, the parallel compression filling algorithm, uses multiple moving tweezers at once to compact the atoms into a dense, perfect grid. A more mathematically sophisticated solution uses something called the Hungarian matching algorithm. This is a powerful optimization tool that calculates the most efficient set of moves for all the atoms, pairing each starting atom with a target site in a way that minimizes their total travel distance and, crucially, avoids them bumping into each other, which could knock them out of their traps. These parallel methods were a huge leap forward. They made it practical to build perfect arrays of many hundreds of atoms, opening the door to more complex quantum simulations. But the most dramatic breakthrough has come just recently, with the integration of artificial intelligence. A team of Chinese researchers led by the renowned physicist Pan Jianwei developed a system that can assemble thousands of atoms simultaneously, and it does so in a nearly constant amount of time, no matter how big the array gets. This new system replaces the old moving tweezers with a device called a high-speed spatial light modulator. This device can project complex holograms, essentially creating a unique light pattern that forms and moves all the optical tweezers at once, each one following its own independent path. The challenge is calculating the thousands of holograms needed for each step of the rearrangement in real time. This is where the AI comes in. The team trained a convolutional neural network on countless simulated atomic arrangements. The AI learned the incredibly complex relationship between where the atoms need to go and the precise hologram required to move them there. The process is astonishingly fast and elegant. First, a camera images the initial random array. Then, the Hungarian algorithm calculates the optimal path for every single atom. The AI then takes over, generating a series of precise holograms that smoothly and simultaneously guide thousands of atoms to their final perfect positions, all while ensuring they don't get heated or lost. Using this AI-driven holographic technique, the team assembled a defect-free array of 2024 atoms in just 60 milliseconds. This is a task that would have taken the previous state-of-the-art methods over a second for a much smaller array. This constant time assembly overcomes the scaling bottleneck that plagued the field for years, providing a clear path to building perfect arrays of tens of thousands of atoms. While building these large, flat 2D arrays is a huge step, the ultimate goal for scaling to the millions of qubits needed for truly powerful, fault-tolerant quantum computers will likely require building in 3 dimensions. Stacking atoms in 3D layers is a way to massively increase qubit density without needing impractically large laser systems. Assembling 3D structures brings new challenges, of course. The atomic cranes have to move atoms not just side to side, but up and down between different planes. Scientists have already achieved this by adding a tunable lens to their setups that can rapidly shift the focus of the moving tweezer. Using this, they've built small, defect-free 3D cubes and other structures containing up to 72 atoms. The new AI-powered holographic technique is also being adapted for 3D, building multi-layered structures by superimposing the holograms for each 2D layer. These are the crucial first steps toward building the large-scale 3D quantum processors of the future. So what is the payoff for all this incredible effort? What can we actually do with these perfect atomic arrays? One of the most immediate applications is quantum simulation. Many deep problems in physics and chemistry, like understanding high-temperature superconductors or designing new catalysts, are too complex for any classical computer to simulate. With these perfect atomic arrays, scientists can build an artificial version of the material they want to study, atom by atom, and observe its quantum behavior directly. For instance, researchers have arranged atoms in a special pattern called a Kagome lattice to create and probe an exotic state of matter known as a quantum spin liquid, a state with massive, long-range entanglement that could be key to building more robust quantum computers. Another application is in quantum metrology, the science of ultra-precise measurement. Entangling the atoms in a defect-free array allows them to make measurements that blow past the limits of classical physics. This has profound implications for technologies like atomic clocks. Using the coherence and entanglement of these arrays, scientists are developing next-generation clocks with unprecedented accuracy, which could improve everything from GPS navigation to fundamental tests of Einstein's theory of relativity. Ultimately, the grand challenge is to build a universal, fault-tolerant quantum computer. Here, defect-free arrays are the essential starting point. The ability to arrange qubits in flexible geometries is crucial for implementing the complex quantum error correction codes needed to protect fragile quantum information from noise. The new AI-powered assembly methods are particularly exciting because they provide a toolbox for active error correction, the ability to detect a lost atom mid-calculation and rapidly bring in a replacement from a reservoir. This dynamic reconfigurability will be an essential feature of future quantum computers. The rapid progress is being driven by a global ecosystem of university labs and innovative companies. Companies like Quera Computing in the US, Pascal in Europe, and Atom Computing are all pushing the boundaries, with Atom Computing recently announcing a system with over 1,000 qubits. These companies are commercializing decades of foundational research and making these incredible machines accessible to researchers and businesses through the cloud. The road ahead is still challenging. Scaling to millions of qubits will likely require a modular approach, networking multiple quantum processing units together, much like a classical supercomputer. The journey to build this new architecture of intelligence is a marathon, a story of taming the quantum world with lasers, algorithms, and now, artificial intelligence. The creation of large, perfectly ordered atomic arrays is more than a technical triumph. It is the laying of the foundation upon which the future of computation will be built. The architects of this quantum realm are hard at work, and the revolution they are building promises to be extraordinary.